This meeting is being recorded.
In section 7 from chapter 10, we are introduced to allylic halogenation now. So another halogenation reaction that is a radical mechanism. And let's take a look here and let's get to know what this allylic halogenation looks like. So the weakest carbon-hydrogen bond is the one with the lowest bond dissociation energy. And this will be the site that undergoes the fastest hydrogen abstraction. So this reaction here listed. So that will be where alkenes would have this halogen abstraction at the allylic carbon. And in our perspective here, that's where the halogenation would occur as well. So let's take a look here. We have a vanillic site that has the highest bond dissociation energy. We have our allylic here. This has the lowest, and then we have another site down here that is neither, and that just has an energy, a bond dissociation energy in between. So amongst these protons, these hydrogens, this one would be abstracted, the allylic site, and therefore alkenes will, we can say, selectively undergo hydrogen abstraction at the allylic carbon. And then that results in halogenation at that site. So this will have the lowest energy because it will generate this resonance stabilized allylic radical. So that's what we see over here, that resonance stabilized radical. That electron is moved with those three curved arrows, and then we see in resonance structure 2 here, we've gone from 1 to 2 by moving 3 electrons, and we've generated this resonance structure. So again, bromination, specifically here in this reaction, would be selective for an allylic carbon. But we have to note that there's also another reaction that if we use Br2, an alkene addition reaction on the pi bond, across the pi bond, right? Remember that reaction from chapter 8? That will be a competing reaction. So a solution to that problem to avoid this competition of reactions would be to use something called NBS, this N-bromosuccinimide down here. And you can see that this bond that I just pointed to with that arrow is the one that's homolytically cleaved to generate our bromide ions. And then we have this resonance stabilized radical over here. So this helps to keep the concentration of both HBr and Br2 low. So we can use this N-bromosuccinimide and that competing reaction from chapter 8, that alkene addition, would be minimized. So let's take a look here at how this happens. If we did this halogenation with NBS during the propagation step specifically, we see that a radical is used, a new radical is generated, and we also create HBr in this first hydrogen abstraction step. Then we have this HBr, which reacts with NBS to form Br2. And this is that self-sustaining reaction that occurs. So then we have, again, this radical here reacts with Br2. We have halogen abstraction in this specific propagation step. And then we have our allylic bromination that results when we have this radical react with this bromine here. And this is also a propagation step, so we produce more of that bromine radical at the end of this step. So you can see that it's a self-sustaining chain reaction as we expect with the propagation step of a radical mechanism. So on this last slide here, we're going to take a look at specifically the allylic halogenation, again, still utilizing the N-bromosuccinimide, but now specifically with these asymmetric alkene. So we have a double bond, and one side is different than the other. So we have a great example here of an asymmetric alkene. We use N-bromosuccinimide. We use light to form our radical, and then we end up with a mixture of isomers, which are often obtained in this case. So one side of the double bond, we add over here our bromine at this tertiary radical site, and then the other side of our double bond, you can see we have this radical delocalization, so movement of that site. So bromination would occur at a primary radical site. So we have this mixture, and again, here's the primary radical that would be brominated here. Our tertiary radical would be brominated here, and we would have this mixture of two isomers as our products, again because of delocalization and the resonance structures. So we will continue with section 10.10 in our next video.